When we look up at the night sky, we see stars, planets, and galaxies shining brightly in the darkness. It might seem like we can see most of what's out there, but the truth is far stranger. Everything we can see, every atom, planet, star, and galaxy makes up less than 5% of the entire universe. The rest is made of two mysterious ingredients that don't give off light or energy the way normal matter does. These invisible components are called dark matter and dark energy, and together, they shape almost everything we see in the cosmos. Even though scientists can't see them directly, their effects are so powerful that without them, the universe as we know it wouldn't exist. Let's start with dark matter. It's the invisible glue that holds galaxies together. Astronomers first suspected its existence nearly a century ago. In the 1930 seconds, a Swiss astronomer named Fritz Zwicky was studying a group of galaxies in a distant cluster. He noticed that the galaxies were moving much faster than they should have been based on the amount of visible matter. If only stars and gas were providing gravity, the galaxies should have flown apart long ago. The fact that they stayed together meant there had to be something else, something invisible, providing extra mass and gravity. Zwicky called it Dunkel Materie, which is German for dark matter. At first, his idea was ignored, but decades later, in the 1970 seconds, another astronomer, Vera Rubin, made detailed measurements of how stars move around the centers of galaxies. She found something surprising. According to Newton's laws, stars farther from the center should move more slowly, just like planets in our solar system. Mercury orbits the Sun faster than Earth, and Earth moves faster than Neptune. But Rubin discovered that stars on the outer edges of galaxies were moving just as fast as those near the center. That didn't make sense, unless there was a huge amount of unseen mass spread throughout the galaxy. This unseen matter was providing the extra gravity needed to keep the fast-moving stars from flying away. Since then, scientists have found even more evidence for dark matter. One of the strongest clues comes from how galaxies bend light. According to Einstein's theory of general relativity, massive objects can warp space and bend light that passes nearby a phenomenon called gravitational lensing. When astronomers look at clusters of galaxies, they often see light from even more distant galaxies stretched and distorted by this effect. But the amount of bending is far greater than what can be explained by visible matter alone. The only explanation is that there must be a large amount of invisible mass in these clusters, dark matter bending the light through its gravity. So what exactly is dark matter made of? That's one of the biggest unanswered questions in all of science. We know it's not made of ordinary atoms, because if it were, it would absorb or emit light, and we would be able to detect it. Instead, it must be made of something entirely different, particles that don't interact much with light or other forms of electromagnetic radiation. Physicists have proposed several possible candidates. One leading idea is that dark matter consists of WIMPs, or weakly interacting massive particles. These particles would have mass and produce gravity, but they would interact so weakly with normal matter that they would pass right through us and the Earth without leaving a trace. Another possibility is that dark matter is made of axions, hypothetical particles that are extremely light but could exist in enormous numbers. Despite decades of research, scientists haven't yet detected dark matter particles directly. Experiments deep underground, where ordinary radiation is shielded, are trying to catch even the faintest signal from a passing dark matter particle. So far, the results have been inconclusive. Some experiments have seen small signals that might be dark matter, but others have not confirmed them. This ongoing search has become one of the biggest challenges in modern physics. If dark matter is found, it could open the door to an entirely new branch of science, one that goes beyond the particles described by the current standard model of physics. Even without knowing what it's made of, scientists can map where dark matter is located by studying its gravitational effects. Using data from telescopes and satellites, astronomers have created large-scale maps showing how dark matter is distributed throughout the universe. These maps reveal that dark matter forms a vast cosmic web, a gigantic network of filaments and clusters that stretches across billions of light years. Galaxies are not scattered randomly. They form along the densest parts of this web, like beads on invisible strings. This structure helps explain why the universe looks the way it does. Dark matter's gravity pulled ordinary matter together, allowing galaxies and stars to form in the first place. Without it, the early universe would have remained a smooth, featureless soup of gas. To understand just how important dark matter is, imagine the early universe. About 13.8 billion years ago, right after the Big Bang. Back then, everything was extremely hot, dense, and nearly uniform. Small fluctuations in density began to grow under the pull of gravity. But ordinary matter couldn't clump together easily because light kept pushing it apart. Dark matter, however, didn't interact with light. It only responded to gravity. That meant it could start forming structures long before normal matter could. Later, as the universe cooled, ordinary matter fell into the gravitational wells created by dark matter. Those wells eventually became galaxies, clusters, and superclusters. So, in a very real sense, dark matter built the cosmic scaffolding on which everything else rests. While dark matter explains the structure and formation of galaxies, another mysterious force, dark energy, controls the universe on much larger scales. Dark energy was discovered much more recently, in the late 1992, when astronomers were studying distant exploding stars called supernovae. These supernovae act like cosmic lighthouses, allowing scientists to measure how fast the universe is expanding. What they found was shocking. Instead of slowing down, as gravity should cause, the expansion of the universe was actually speeding up. something unseen was pushing galaxies apart, working against gravity. That unknown force became known as dark energy. Dark energy makes up roughly 68% of the total energy in the universe, while dark matter makes up about 27%. Everything else, all stars, planets, gas, dust, and living beings, adds up to less than 5%. That means almost everything in the universe is something we can't see or touch. Yet, its effects shape the destiny of the cosmos. If dark energy continues to drive expansion, the universe will keep stretching faster and faster, eventually becoming cold and empty as galaxies move so far apart that they can no longer see one another. Scientists still don't know what dark energy is. Some believe it's a property of space itself, a constant energy that fills every part of the universe, even empty space. This idea goes back to Einstein, who once introduced something he called the cosmological constant to keep his equations from predicting an expanding universe. Later, he called it his biggest mistake, but it may turn out to be real after all. Others think dark energy could be something dynamic, like a new kind of field that changes over time, similar to how the electromagnetic field works. Still others suggest it might indicate that our understanding of gravity is incomplete. What makes dark energy so mysterious is that we can't detect it directly. We can only infer its presence from the way the universe expands and evolves. Yet its influence is enormous. Over billions of years, it has come to dominate the universe's behavior. In the distant past, gravity from dark matter slowed expansion, allowing galaxies to form. But as the universe grew and spread out, dark energy became stronger, pushing everything apart more rapidly. Today, dark energy controls the universe's fate. Even though dark matter and dark energy are often mentioned together, they're not the same thing. Dark matter pulls things together through gravity, while dark energy pushes them apart. One holds the universe together, the other tears it apart. Their interaction determines how the cosmos grows, changes, and ultimately ends. Scientists are still trying to figure out whether these two mysterious components are related or completely separate phenomena. The study of dark matter and dark energy is not just about explaining the universe, it's also about understanding our place within it. We live in a tiny bubble of normal matter, surrounded by an ocean of invisible forces that we barely comprehend. Yet these unseen ingredients are the reason galaxies exist, stars shine, and planets like Earth can form. The mystery of dark matter and dark energy reminds us how little we truly know and how much there is still left to discover. When scientists discovered that most of the universe is made of dark matter and dark energy, it completely changed how we think about everything. Before the 20th century, people believed the cosmos was mostly made up of stars, planets, and gas. The things we could see, but the more we looked, the more it became clear that what's visible is just a small piece of the puzzle. Imagine an iceberg floating in the ocean, The shiny tip is the visible universe, while the massive hidden portion beneath the water represents dark matter and dark energy. These hidden forces shape the universe on every level, from the smallest galaxy to the entire cosmos. Let's look more closely at dark matter first, because it's a little easier to understand than dark energy. Scientists can't see it directly, but they've built up a detailed picture of what it does. It doesn't shine, absorb, or reflect light. It doesn't interact with electromagnetic forces the way normal matter does. But it does have mass, and that means it creates gravity. This gravity affects how galaxies move, how light bends, and even how the universe evolved after the Big Bang. Because it doesn't collide or clump together like ordinary matter, dark matter forms smooth, extended halos around galaxies instead of flat disks. These halos are crucial because they keep galaxies from tearing themselves apart. If we could somehow remove dark matter from a galaxy, the stars would no longer be held tightly by gravity. They would quickly scatter into space. In fact, every galaxy, including our Milky Way, is surrounded by a huge, invisible sphere of dark matter that contains far more mass than all the stars, planets, and gas combined. That's why astronomers say we live in a dark matter-dominated universe. Even though we can't see it, it's everywhere, silently shaping the motion of everything we can see. Modern telescopes and computer simulations have helped scientists visualize how dark matter shaped the universe after the Big Bang. In the earliest moments, matter was spread out almost evenly, with only tiny differences in density. Over time, the slightly denser regions began to pull in more material through gravity, forming clumps. Dark matter, being unaffected by light or radiation, started clumping first. Ordinary matter, mostly hydrogen and helium, later fell into these clumps, forming the first stars and galaxies. As billions of years passed, these clumps merged to form larger and larger structures. What emerged was a vast cosmic web made of long filaments of dark matter, with galaxies strung along them like pearls on a thread. We can actually observe traces of this web through the light of distant galaxies. The way that light bends and stretches as it travels through space tells us where dark matter lies along its path. This technique, called weak gravitational lensing, allows scientists to map dark matter even though they can't see it. These maps show that dark matter isn't evenly spread out. It's concentrated in certain regions, especially around galaxy clusters, which act like giant knots in the cosmic web. The areas between these filaments are relatively empty, forming vast cosmic voids where few galaxies exist. In some galaxy clusters, astronomers have even seen direct evidence of dark matter separating from normal matter during massive collisions. A famous example is the Bullet Cluster, a pair of galaxy clusters that collided hundreds of millions of years ago. When they crashed, the hot gas from each cluster slowed down and got stuck in the middle because gas interacts and heats up. But the dark matter from each cluster passed right through without colliding, continuing on its way. By observing the gravitational lensing in the aftermath, scientists could see that the dark matter had separated from the visible gas. This provided one of the strongest pieces of evidence that dark matter really exists and isn't just a mistake in our understanding of gravity. But what exactly is dark matter made of? That question remains unsolved. Physicists have tried many approaches to find out. Some experiments use ultra-sensitive detectors deep underground, often in old mines or mountains, to block cosmic rays and radiation that might interfere with the search. These detectors are filled with special materials that can produce tiny flashes of light or vibrations if a dark matter particle happens to collide with an atom inside. So far, the results have been frustrating. No clear detection has been made. Still, every experiment helps narrow down what dark matter could be. There are several competing theories. The leading candidate for many years was the WIMP, the weakly interacting massive particle. WIMPs were thought to fit naturally into theories that extend beyond the standard model of particle physics. If they exist, they would have been produced in large quantities in the early universe and would move slowly enough to clump together, forming the dark matter we see today. But after decades of searching, no evidence for WIMPs has been found. So scientists are exploring other possibilities. One idea involves very light particles called axions. These are hypothetical particles that could exist in enormous numbers, filling space like a background fog. If axions are real, they could account for the missing mass in the universe. Another idea suggests that dark matter could consist of primordial black holes, tiny black holes, formed in the earliest moments after the Big Bang, much smaller than the ones made by stars. These black holes would act like invisible clumps of mass, providing the same gravitational pull as dark matter. However, observations so far have not confirmed this either. There's also a more radical idea. Maybe dark matter doesn't exist at all, and the problem lies in how we understand gravity. Some scientists propose modifying the laws of gravity so that they behave differently on large scales. This idea, known as modified Newtonian dynamics, MOND, can explain some galaxy rotation curves without requiring dark matter. However, it doesn't fit all the evidence, especially the gravitational lensing and galaxy cluster data. So most scientists still believe dark matter is real. Regardless of what dark matter turns out to be, it clearly plays a huge role in shaping the universe. Without it, galaxies wouldn't have formed the way they did, and the universe would look completely different. But as mysterious as dark matter is, it's only half the story. The other half, dark energy, is even stranger. Dark energy wasn't discovered until 1998, when two separate teams of astronomers were studying distant supernovae to measure how fast the universe was expanding. They expected to find that expansion was slowing down because gravity should pull everything together over time. Instead, they found the opposite. the expansion of the universe was speeding up. That discovery shocked the scientific community and led to one of the greatest mysteries in modern cosmology. To explain this accelerated expansion, scientists propose that there must be a form of energy spread throughout space that acts like a repulsive force. Unlike dark matter, which clumps together due to gravity, dark energy does the opposite. It pushes space apart. Its effects are very small on a local scale, but over vast distances, they dominate the universe's behavior. Today, dark energy is thought to make up about 2/3 of the total energy in the cosmos, meaning it's the most important factor determining the universe's fate. What could dark energy be? One simple explanation is that it's a property of space itself, a constant energy density that doesn't change as the universe expands. This idea fits Einstein's cosmological constant, which he first introduced in 1917. At the time, he wanted to describe a static universe. But later, when the expansion of the universe was discovered, he dropped the constant and called it his biggest blunder. Ironically, modern evidence suggests that he might have been right after all, though for reasons he never imagined. Another idea is that dark energy isn't constant, but changes over time, like a slowly evolving field called quintessence. If that's true, dark energy could have different effects in the past and future, possibly even reversing its behavior someday. There are also theories that suggest dark energy might not exist at all. Instead, what we see as accelerated expansion could be the result of our misunderstanding of gravity on cosmic scales. However, all current observations support the idea that something is indeed driving the universe apart, and dark energy remains the best explanation. Measurements from cosmic microwave background radiation, galaxy surveys, and supernova studies all point to a universe dominated by this mysterious force. Even though dark energy works on scales far beyond human experience, it affects everything, including our future. Over billions of years, it will determine how the universe evolves. If dark energy remains constant, galaxies will continue moving apart faster and faster, eventually disappearing from each other's view. Stars will burn out, and the cosmos will grow cold and dark, a scenario called the Big Freeze. If dark energy grows stronger over time, it could eventually rip apart galaxies, stars, planets, and even atoms in a final event called the Big Rip. On the other hand, if dark energy weakens or reverses, gravity could one day overcome it, causing the universe to collapse in a big crunch. No one knows for sure which outcome will happen. The only thing we can say with confidence is that dark energy is real, and it's shaping the future of everything. The discovery of dark matter and dark energy has changed the way we think about the universe forever. It showed that what we see, the stars, galaxies, and light, only tells a tiny part of the story. The rest of the universe is hidden, invisible, and mysterious. but still has powerful effects that we can measure. What's fascinating is that even though we can't see dark matter or dark energy directly, we can trace their fingerprints everywhere. The movement of galaxies, the bending of light, and even the background glow left over from the Big Bang all carry clues about these unseen forces. Let's talk more about the cosmic background radiation, because it's one of the most important pieces of evidence we have. The cosmic microwave background, or CMB, is the faint afterglow of the Big Bang. It fills the entire universe and can be detected in every direction as a low, uniform microwave signal. Scientists study tiny variations in the temperature of this radiation to understand what the early universe was like. These temperature differences are incredibly small, only about 1 part in 100,000, but they contain vital information about how matter and energy were distributed just 380,000 years after the Big Bang. When scientists analyzed the CMB data, they found something striking. The universe's overall composition could be measured with great precision. The results showed that only about 5% of the universe is ordinary matter, while roughly 27% is dark matter, and around 68% is dark energy. These numbers matched perfectly with what astronomers had already seen through galaxy motion and supernova studies. That meant the idea of dark matter and dark energy wasn't just a guess, it was confirmed by independent evidence from completely different parts of science. The CMB also helps us understand how dark matter works in the early universe. The tiny ripples seen in the CMB show where matter was slightly denser, and those regions later became the seeds of galaxies. But if there were only normal matter, those ripples wouldn't have grown fast enough to form the galaxies we see today. Dark matter provided the extra gravity needed to speed up the process. Because it doesn't interact with light, dark matter could start forming structures much earlier, long before ordinary matter could cool down enough to clump together. Without dark matter, the universe today would still be mostly smooth, with few stars or galaxies. The CMB also offers clues about dark energy, though in a more subtle way. The way the light from the early universe spreads out and reaches us tells scientists how the expansion rate of the universe has changed over time. By comparing the observed patterns in the CMB with those in galaxies and supernovae, scientists can tell that expansion has been accelerating in recent cosmic history. This acceleration fits perfectly with the idea of dark energy, a mysterious force that causes space itself to stretch faster and faster as time goes on. Even though we know dark energy exists, it's one of the hardest things to study. That's because it doesn't clump together like matter, and it doesn't emit or absorb light. Instead, it affects the large-scale geometry of the universe. One way scientists study it is by looking at something called the cosmic distance ladder. This involves measuring distances to galaxies in different ways, using nearby stars, then supernovae, and then the overall expansion of space to see how fast the universe has been expanding at different times. When they plot these measurements, they see a clear curve showing that expansion is speeding up. not slowing down. Astronomers also study something called baryon acoustic oscillations, which are faint patterns left over from sound waves that moved through the early universe. These ripples created slight overdensities where galaxies later formed. By measuring how far apart these galaxies are today, scientists can tell how much the universe has expanded since then, providing more evidence for dark energy. Despite all these clues, dark energy remains a mystery. Some scientists think it's a constant energy built into the fabric of space. Others suspect it's changing over time, possibly connected to quantum fields. There are even theories that suggest our universe is just one part of a larger multiverse, and that dark energy varies between different universes. These ideas may sound like science fiction, but they're grounded in real mathematics and cosmological models. Interestingly, dark energy may also help explain why the universe is so flat. When scientists talk about the universe being flat, they don't mean it has edges like a table. They mean that, on the largest scales, the geometry of space follows the rules of flat geometry, rather than being curved. Measurements of the CMB show that space is very close to perfectly flat. This balance suggests that the total amount of energy and matter in the universe adds up just right, including dark energy. If dark energy were missing, the universe's geometry wouldn't match what we observe. Another exciting area of research involves how dark energy affects the fate of the universe. Right now, galaxies are moving away from each other, and the rate of expansion is accelerating. If dark energy remains constant, this acceleration will continue forever. Over trillions of years, galaxies will drift so far apart that their light will no longer reach each other. Future observers, if any exist, will live in a dark, empty universe where other galaxies are invisible and the cosmos appears lonely and still. If dark energy becomes stronger over time, the effects would be far more dramatic. At first, galaxies would separate faster. Then, stars and planets might be torn apart. In the final stages, atoms themselves could be ripped apart in what scientists call the Big Rip. This extreme scenario depends on the nature of dark energy, and while most evidence suggests it's not happening anytime soon, it's still possible in some theories. On the other hand, if dark energy weakens, the expansion could eventually slow down. Gravity might then take over, pulling everything back together. That would lead to a big crunch, where the universe collapses into a hot, dense state again. Some scientists even speculate that a new Big Bang could follow, creating a cyclical universe that expands and contracts over and over. To figure out which of these futures is correct, scientists are studying how dark energy behaves over time. Projects like the Euclid Space Telescope, launched by the European Space Agency, and NASA's Nancy Grace Roman Space Telescope, are designed to map billions of galaxies with extreme precision. By seeing how galaxies are distributed and how fast they move away, astronomers can learn more about how dark energy has changed through cosmic history. In addition to telescopes, scientists also use massive computer simulations to test different models of the universe. These simulations track billions of particles and galaxies over billions of years, showing how structures evolve under various assumptions about dark matter and dark energy. By comparing the results with real observations, they can test which theories make sense and which don't. These models are so detailed that they can reproduce the large-scale structure of the universe almost exactly, showing how dark matter forms filaments, how galaxies cluster, and how dark energy affects their spread. What's remarkable is that even though dark matter and dark energy are invisible, their presence can be seen everywhere once you know what to look for. When we see galaxies spinning too fast, that's dark matter. When we see space stretching faster than it should, that's dark energy. These two invisible forces control nearly everything, yet we only learned about them in the last century, a reminder of how much we still have to discover. Some scientists like to say that studying dark matter and dark energy is like trying to understand the ocean by only looking at the foam on the waves. We can see the surface, the stars, and galaxies, but the deep, invisible parts hold most of the mass and energy. That comparison helps us remember how small our understanding really is, but it also motivates us to explore further. Today, physicists and astronomers all over the world are working together to uncover the nature of these mysterious forces. Every new observation, every experiment, brings us one step closer to understanding the true makeup of the cosmos. Even though the answers remain hidden for now, the search itself is one of the most exciting adventures in science. The more scientists learn about dark matter and dark energy, the more they realize how deeply these mysteries are connected to every part of the universe's history. They affect everything from the birth of galaxies to the ultimate fate of space itself. It's hard to imagine that something we can't see or touch could have such a massive influence, but the evidence is undeniable. Even the simplest observations, like the way galaxies move or how light bends through space, can't be explained without them. Let's look again at dark matter, because it plays the role of a silent architect in the cosmos. Imagine you're looking at a map of the night sky filled with billions of galaxies. Each one of those galaxies is like an island of stars, surrounded by an invisible ocean of dark matter. This dark matter extends far beyond the visible parts of galaxies 10 or even 100 times farther than the light from their stars. It creates huge halos of gravity that keep galaxies stable. We know this not just from galaxy rotation, but also from galaxy clusters. A single galaxy's dark matter halo helps keep its stars together. But galaxy clusters, groups of hundreds or thousands of galaxies, also have massive dark matter envelopes binding them as a whole. When scientists study how fast galaxies move within a cluster, they find that there must be far more mass there than we can see. The visible galaxies and gas account for only a small fraction of the total mass. The rest must be dark matter. Another incredible discovery comes from how light behaves when passing through these massive clusters. According to Einstein's general relativity, mass bends space, and light follows that curvature. When light from distant galaxies passes near a massive cluster, it gets distorted and stretched, a phenomenon called gravitational lensing. Sometimes, this bending is so strong that it creates multiple images of the same galaxy, or beautiful arcs of light called Einstein rings. By studying these distortions, scientists can create maps showing where the invisible mass, the dark matter, is concentrated. It's like taking an X-ray of the universe's skeleton. These maps show a striking pattern. The distribution of dark matter lines up with where galaxies form. This confirms that dark matter provides the structure on which normal matter builds. Without dark matter, there wouldn't be enough gravity to pull gas and dust together to make stars and galaxies. The universe would be much emptier and smoother than it is today. Even though dark matter doesn't emit light, scientists have found clever ways to detect its presence indirectly. One way is by studying the hot gas that fills galaxy clusters. This gas glows brightly in X-rays and is incredibly hot, millions of degrees. By measuring how hot it is and how it moves, scientists can calculate how much gravity must be holding it in place. The numbers only make sense if dark matter makes up most of the cluster's mass. Another way is through the motion of satellite galaxies, small galaxies that orbit larger ones, like moons, around planets. Their orbits reveal how much mass is present, and again, the results show far more mass than visible matter alone can explain. Even our own Milky Way galaxy has satellite galaxies, like the Large and Small Magellanic Clouds. The way these galaxies move and the way stars in the Milky Way's outer regions travel both confirm that our galaxy is surrounded by a vast halo of dark matter. Scientists estimate that for every bit of normal matter in the Milky Way, there's at least 5 times as much dark matter. Without it, the Milky Way would fly apart, instead of remaining stable for billions of years. To get an even clearer picture, scientists have created massive computer simulations that try to reproduce how the universe grew from the Big Bang to today. These simulations start with the known laws of physics and a certain amount of dark matter and dark energy. Over billions of simulated years, matter clumps together under gravity, forming filaments, clusters, and voids. The results look astonishingly similar to what we observe through telescopes. That agreement gives scientists confidence that they're on the right track, even if they don't yet know what dark matter actually is. These simulations also show how delicate the balance between dark matter and dark energy really is. In the early universe, dark matter's gravity dominated, pulling matter together and forming galaxies. But as the universe expanded and grew larger, the influence of dark energy began to increase. Today, dark energy dominates the universe's behavior, pushing galaxies apart faster and faster. This cosmic tug-of-war between the pulling force of dark matter and the pushing force of dark energy defines everything about the universe's past, present, and future. One fascinating question scientists often ask is whether dark matter and dark energy might be connected. At first, they seem completely different. One pulls, the other pushes, but both are invisible. and both affect the universe through gravity. Some theories suggest they could be two sides of the same coin, possibly connected through deeper physical laws that we don't yet understand. Maybe they both come from the same hidden field of energy that fills space. Or maybe our current understanding of gravity is incomplete, and what we call dark matter and dark energy are actually signs that we need a new theory of the universe. For example, Einstein's general relativity has passed every test within the solar system, but we don't know if it's perfect on the largest cosmic scales. Some scientists have proposed extensions to relativity that could explain both dark matter and dark energy as side effects of how space-time itself behaves. Others think that extra dimensions beyond the three we experience could influence gravity in ways that look like dark matter or dark energy to us. These ideas are difficult to test, but future telescopes and experiments may provide answers. The universe gives us plenty of natural laboratories to study these mysteries. One of the most useful is the study of merging galaxy clusters. When two clusters collide, normal matter, which includes hot gas, slows down and heats up, while dark matter passes through unaffected. This separation allows scientists to compare the visible and invisible components directly. The famous bullet cluster is a perfect example, but many others have been discovered since. Each one offers more evidence that dark matter behaves differently from ordinary matter and interacts only through gravity. There's also a newer, even stranger possibility that dark matter might not be completely dark. Some scientists think it could interact with itself through unknown forces. In other words, dark matter might have its own type of dark physics, including particles that attract or repel each other, similar to how atoms interact through electromagnetism. If that's true, there could even be dark atoms, dark stars, or dark galaxies made entirely of invisible material. These would exist alongside our own, completely undetectable, except through gravity. It's an exciting idea that expands our imagination about what might be out there. At the same time, dark energy continues to puzzle everyone. It doesn't clump, it doesn't attract, and it doesn't emit radiation. It's simply there, everywhere, and it's incredibly uniform. Its energy density seems to stay constant even as the universe expands, which doesn't make sense according to normal physics. If you spread matter out over a larger space, its density drops. But dark energy doesn't seem to behave that way. It's as if new dark energy appears as more space is created, keeping its density steady. That strange property is one of the reasons dark energy might be linked to the fabric of space itself. Some scientists even connect dark energy to quantum physics. In quantum theory, empty space isn't really empty. It's filled with tiny fluctuations that appear and disappear constantly. These fluctuations have energy called vacuum energy. When physicists calculate how much vacuum energy there should be, the result is unbelievably huge, much greater than what we actually observe as dark energy. The fact that the real universe's expansion is much slower means that something cancels out most of this energy, leaving just a small leftover amount that drives cosmic acceleration. No one knows why this happens, but solving that mystery could reveal new truths about the link between quantum mechanics and gravity, two areas of physics that don't yet fit together perfectly. The idea that empty space can have energy may sound bizarre, but experiments have already shown that quantum fluctuations are real. In laboratory settings, they can cause tiny measurable forces between objects, known as the Casimir effect. So it's possible that what we call dark energy is the large-scale effect of those same quantum phenomena happening everywhere in the universe. If that's true, dark energy isn't something new. It's a feature of reality that's always been there, waiting for us to notice. No matter what dark energy turns out to be, one thing is certain. It controls the fate of the cosmos. The balance between dark matter's gravity and dark energy's repulsive force determines how the universe will end. And right now, dark energy is winning. To understand how deeply dark energy and dark matter influence the universe, it helps to think of them as cosmic forces that have been shaping everything since the very beginning of time. Right after the Big Bang, about 13.8 billion years ago, the universe was extremely hot, dense, and filled with energy. As it expanded, it began to cool, allowing the first particles, atoms, and eventually light to form. In those early moments, tiny variations in density created the seeds for everything that exists today. But without dark matter, those small clumps of matter wouldn't have had enough gravity to grow into galaxies and stars. In the first few 100,000 years after the Big Bang, radiation dominated the universe. Normal matter, like protons and electrons, couldn't easily come together because light pushed them apart. But dark matter didn't interact with light, so it wasn't affected by that pressure. It could start gathering under its own gravity, forming invisible clumps that would later attract normal matter. As the universe continued to expand and cool, hydrogen and helium gas began to fall into these dark matter wells, eventually forming the first stars. Those stars lit up the universe for the first time, ending the cosmic dark ages. The first galaxies that formed were small and irregular, but they grew over billions of years by merging and attracting more material. Computer simulations show that this process follows the patterns created by dark matter. Galaxies formed where dark matter was densest, along the filaments of the cosmic web. This explains why galaxies aren't spread evenly across the sky, but are grouped into clusters and superclusters, separated by enormous empty voids. It's as if dark matter laid down the scaffolding of the universe, and normal matter just filled in the gaps. Today, astronomers can even measure how much dark matter exists inside galaxies by studying their rotation. For example, when scientists measure how fast stars orbit the centers of galaxies, they find that the outer stars are moving much faster than expected. If only visible matter were present, those stars should have much slower speeds or they'd fly off into space. The only explanation is that there's an invisible halo of dark matter extending far beyond the visible edge of the galaxy, holding everything together through gravity. This dark matter halo isn't uniform, it's thicker in some areas and thinner in others. Within it, galaxies like ours formed their spiral arms and central bulges. Our own Milky Way is believed to have a dark matter halo stretching at least 1 million light-years across. That means our solar system is swimming through dark matter right now, though it's spread so thinly that we never notice it. Billions of dark matter particles may be passing through your body every second, yet they rarely, if ever, interact with normal atoms. Scientists are building extremely sensitive detectors to catch these elusive particles. Deep underground laboratories, buried under mountains or inside old mines, house tanks filled with liquid xenon or other materials that can flash or vibrate if hit by dark matter. These experiments have to be shielded from cosmic rays and natural radioactivity so that no false signals interfere. Despite decades of searching, no one has conclusively detected a dark matter particle yet, but new experiments are being designed all the time. If scientists do eventually find dark matter particles, it will be one of the most important discoveries in history. It would confirm that most of the universe's mass is made of something entirely new, something beyond the physics we currently understand. It could also reveal a hidden world of particles and forces that operate alongside our own, unseen but fundamental to existence. Meanwhile, dark energy presents an even greater challenge. Unlike dark matter, which pulls through gravity, dark energy pushes outward, driving the acceleration of the universe's expansion. To understand how it works, scientists often describe the universe as a kind of stretching fabric. When you stretch a piece of fabric, the space between the threads increases. Similarly, as the universe expands, the space between galaxies grows. Dark energy is what's causing that expansion to speed up instead of slow down. We can measure this expansion through something called the Hubble constant, which tells us how fast galaxies are moving away from us based on their distance. Edwin Hubble discovered this relationship in the 1,920 seconds, showing that the universe is expanding. But in the late 1,990 seconds, observations of distant supernovae revealed something unexpected. The rate of expansion wasn't decreasing over time. As gravity would suggest, it was increasing. That was the moment dark energy entered the picture. Since then, scientists have tried to measure the Hubble constant as precisely as possible, using different methods. But here's where things get strange. When we measure it by looking at nearby galaxies and supernovae, we get one number. When we measure it by studying the cosmic microwave background, we get a slightly different number. This disagreement, known as the Hubble tension, might be a clue that something about our understanding of the universe, perhaps dark energy itself, is incomplete. One possibility is that dark energy has changed over time. In the early universe, it may have been weaker, allowing matter to clump and form galaxies. As space expanded, dark energy could have become stronger, gradually taking over and accelerating expansion. If this is true, it would mean that dark energy isn't a fixed constant, but a dynamic field that evolves with time. Scientists call this idea quintessence, borrowing the term from ancient philosophy that described a mysterious fifth element filling the heavens. To study this, researchers use large-scale surveys of galaxies and cosmic structures. By measuring how galaxies cluster and how their light is stretched by cosmic expansion, they can map how dark energy has influenced space throughout time. Projects like the Dark Energy Survey, DES, the Euclid mission, and the Roman Space Telescope are designed to do exactly that. These projects collect enormous amounts of data, billions of light measurements, allowing scientists to track how dark energy affects the growth of the universe at different epochs. Another method involves studying how galaxies move within massive clusters. If dark energy is changing over time, it could subtly affect how these clusters grow and how galaxies fall into them. Even small variations could provide hints about the true nature of dark energy. That's why modern astronomy isn't just about taking pictures of space. It's about measuring, mapping, and comparing the universe with incredible precision. Dark energy is not only shaping the present, but also deciding the universe's future. If it remains constant, galaxies will continue to move away from each other forever. Over trillions of years, stars will burn out, new stars will stop forming, and the universe will fade into a cold, dark, empty expanse. This is called the Big Freeze, or heat death scenario. It's not a dramatic ending, it's more like a slow fading away. But if dark energy grows stronger, its effects could become catastrophic. In that case, the repulsive force could eventually overcome gravity at every scale. Galaxies would be torn apart, then solar systems, then planets, and finally atoms themselves. This ultimate end is known as the Big Rip. The timeline for such an event would depend on how fast dark energy increases, but it would take billions of years before anything like that could happen. There's also the opposite possibility that dark energy could weaken or even reverse. If that happens, gravity could eventually stop the expansion and pull everything back together in a big crunch. In that scenario, galaxies would start moving toward each other, merging into giant structures until the universe collapses into a single point. Some theories even suggest that this could lead to a new Big Bang, starting the cycle over again. No matter which outcome turns out to be true, dark energy is the key. It determines whether the universe will expand forever, tear itself apart, or collapse back in on itself. And since it makes up about 68% of everything, it's fair to say that dark energy holds the universe's fate in its hands. The idea that something so invisible could decide the destiny of all matter and light is both humbling and thrilling. It reminds us that even though we've learned so much about the universe, we've only scratched the surface of its mysteries. The deeper we look, the more questions we find questions about what reality is made of, how space and time really work, and whether there are hidden layers of existence that we can't yet detect.